So in molecular and cellular biology, as we study biomacromolecules, we want to consider lipids. And lipids are bundles of hydrocarbons. This is the one class of biomacromolecules that we're going to look at that is not a true polymer. Now, when I think of lipids, the more conventional term is fats. So we think about plant oils, we think about margarine, we think about butter, we think about frying things in fat. And in general, this tastes very good to us because fat is very, very high in energy. And from an evolutionary point of view, our body rewards us for eating fat with that good taste because we need calories to live. We evolved in an environment where calories weren't necessarily easy to come by. Now, this particular recording, I want to focus on the idea of hydrophobic and hydrophilic, because lipids, being primarily hydrocarbons, usually are almost entirely hydrophobic, or a good portion of the molecule is hydrophobic. So as we move through the material and study lipids more, we're going to talk about fats specifically, phospholipids, which are amphipathic molecules. They are both hydrophobic and they have a section that's hydrophilic. And then, of course, steroids. Now, I keep using these terms hydrophobic and hydrophilic, so we need to address them now because they're going to be one of the fundamental concepts that we're going to need to understand how cells form. It's going to drive protein folding. It's going to drive a tremendous amount of the basic biology. So hydro, again, is water. Philic is loving, and phobic is fear. Think of phobias, or fearful. So molecules that are hydrophobic tend to not mix with water. So they fear water. So think about how you would pour oil into water, and ultimately you see all the water and oil separate from each other. Right? Now, why is this? We need to understand this so we understand the origin of hydrophobic forces. Let's go back to water. We've talked about water before in earlier recordings, and we know that water is a polar substance, and that the nature of that polarity, having partial positive and partial negative charges, leads to the formation of hydrogen bonds. And that hydrogen bonding network is what we call a flickering lattice. Right? It is transient. It's in motion. It's satisfying a positive and a negative who want to be together, but because of the energy of the system, those molecules are moving past each other, and it reforms and reforms very, very short time frame. Right? So this then we can measure as entropy. So I'm going to introduce this term entropy, and this is a disorder. So we can measure disorder to a certain extent. And this transient flickering lattice is highly disordered in that respect. So we talked about as water moves and becomes ice, we have to order that lattice and hence expand the water. It becomes less dense to maintain positive-negative relationship between the sides of those molecules. But in liquid water, this disorder is high. Now, the second law of thermodynamics, so again, remember, physics is one of the foundational sciences upon which biology is built. We don't have special rules. We have to understand physics. We have to understand thermodynamics. So we're going to talk more about the second law of thermodynamics later, and thermodynamics in general, as we talk about energy and metabolism. But for now, we need to understand that the second law of thermodynamics basically is that the universe is moving towards disorder. That the disorder of a system is going to increase for things that happen spontaneously, like water and oil separating. I didn't have to put energy into that system to see it happen. Right? So this results in what's called the hydrophobic effect, when we have highly hydrophobic molecules interacting with an aqueous environment. Right? Remember, water wants to be with water because water is polar. Hydrocarbons, as we mentioned earlier, are almost completely nonpolar. Right? So what does that mean? It means that carbon and hydrogen have almost the exact same electronegativity. Right, so we're reviewing concepts we talked about earlier. You need to go back and listen to that stuff again, read about it again if you're like, oh yeah, electronegativity, what the heck is he talking about? So the tendency for those atoms to pull electrons to themselves is exactly the same, or nearly so, with hydrogen and carbon, and so they're sharing those electrons equally, hence they don't have charge. Now, if you put something without charge next to something with charge, charge is looking for the opposite charge. You're not doing anything for that molecule looking for charge if you have no charge. So what we see then is the water, or all those molecules that are polar, want to minimize their contact with the molecules that are nonpolar, right? So literally, this is one of my favorite pictures to depict this. You force, in essence, all the hydrophobic or nonpolar molecules together to minimize the interface. Because at that interface, you're going to have to order the water molecules so they can satisfy their positive and negative interactions. And that order wants to be minimized because of the second law of thermodynamics. Right? So if we force more order into the system, we don't want to go in that direction. Rather, we minimize the order we've introduced to the system by separating the water and the oil. All right? So this is an idea that we're going to see is going to drive the formation of bilayers or cell membranes later in the quarter, and that's going to be the foundation of cells, and we know that cells are the fundamental unit of life. So this concept is very important. We'll come back to it again and again.